Welcome everybody. So this is our presentation to this speed dating workshop. With our one, I mean Jesper Swedenberg. He is Professor of Vascular Surgery at KI. He is here today. Then Joy Roy, Vascular Surgeon at KI. Martin Auer, software developer at a very small Austrian company. And myself, I'm with the Department of Solid Mechanics, so Hollfastetslehre. And to some extent, our mission is given by the title here. So we want to integrate finite element simulations, structural biomechanical simulations in a clinical workflow, particularly of abdominal aortic patients. Well, of course, that needs some explanation here, and that's illustrated here. So we think, and it's not just we, so all other groups do think that biomechanics could play an important role integrated in a clinical decision-making process here. The particular case here is an aneurysm patient, where you see down here, you have a huge enlargement of the aorta. This is the aneurysm, or AAA. And now the clinical team has to take the decision, what's the best treatment for this patient, right? Particularly because this might rupture if it grows too large, and if the main blood supplying pipe in your body bursts, then you can imagine this is some kind of situation. That runs then, based on this information, we built a computational model, and this computational model is then able to predict something. And the something what we predict here is tension in the wall, because the tension in the wall will give a better idea if this will rupture or not. And based on this information, we then can justify such an intervention or not. Critical point, of course, here is the computational model. A computational model has to be a simplification, and the question is how simple can that be in order to be useful, still to be useful. Now this slide here is a bit complicated. I will just put it down here like that. It should illustrate the real interdisciplinary field we are working here. So what we need is we need mechanical testing, in vitro testing, which we do at our department. Of course, the specimen comes from the surgical team. Then we need to do microscopy, again at KI or at KTH. And then we have to build up complex mathematical models in order to predict what actually our test is telling us. This is then entering our computational model, gets enriched by geometry of the patient. Here we need, of course, image reconstruction and particular patient data. And all this information is then processed in a software which we have developed, which is called A4 Clinics. And simply what this software is doing, so you're gonna input computed tomography angiography data, patient data like blood pressure, gender, and so forth. Then this information is processed, and eventually you end up with measurement or geometrical properties like the maximum diameter. So this is not very complicated, but this new parameter, peak wall rupture risk, this is something which can tell you how close the tension in the wall is to the rupture of the wall. And now we get in the next mess. So how you're going to explain what peak wall rupture risk is to a vascular surgeon, right? So we are not equipped with financial material to run longitudinal studies to investigate at which peak wall rupture risk intervention is not justified. So what we did here is we're going to map back our complicated parameter peak wall rupture risk to something which is known by the clinicians, which is maximum diameter. I will not go into detail how this procedure works, but it's one critical part. If you come up with very innovative technology, at the end of the day, you have to come down and tell in our case, the vascular surgeon, what this is good for. 1 minute? Yeah. Okay, that's fine. So for detailed information, you better visit our website. And I will go back to this first image here in order to define our needs. So what are actually our needs? I mean, we're working in a very fine setting, and to some extent we are satisfied. But one problem here in this picture is that this arrow here enters mean population data in our patient-specific analysis, right? So we have to use mean patient information regarding the elasticity of vascular tissue. And there it would be one chance to add another arrow here, which is functional imaging. So perhaps we can explain the large variability in test data by including information from functional imaging. And if we would have a strong group of functional imaging, perhaps we could reduce the error which enters due to this error in our simulation. So thank you for your attention.